Hello, this is Jack Jackson, and in this video we're going to be introducing and investigating the fundamental theorem of calculus. This is one of the greatest achievements in mathematics of all times, actually. And so, as its name suggests, fundamental theorem of calculus, this is going to be a very fundamental or central idea in calculus, and in fact it's going to actually connect the two big parts of calculus, integral calculus and differential calculus, the study of the definite integral and the study of the derivative. And these are going to be connected together by this fundamental theorem. Okay, so to start this, let's look at this graph of f of t equals 3t squared, and we're going to look at that. Let's graph it on the interval 0 to 4. So let's see, that's an increasing function on that interval. It increases from t equals 0 and y f is 0 to t equals 4, and 4 squared is 16 times 3, that's about 48. So I used a window to start with, at least from 0 to 50 for y and 0 to 4 for x. In fact, I may later on go into the negatives just a little bit just to give some space at the bottom of the screen, but that's going to be a window. So go ahead and get that on your calculator. This is going to make some use of a graphing calculator here, and you'll have some screenshots from a TI-84 here. So if you've got a TI-84 or some other graphing calculator, see if you can follow along with me. So kind of get caught up to here, and we want to consider the function a of x is the integral from 0 to x of f of t dt. That is the integral from 0 to x of 3t squared dt. So here's the first question. This is going to be a series of tasks and questions that we're going to go through here. And so I'm going to stop at each point and ask you to do something, and then you're going to check your work against what I do in the video. So it's kind of an inquiry-based project that we're going to work through together here. So how can we visualize a of x, which is this integral from 0 to x of 3t squared dt for different values of x? And by the way, we could have just said, could have left this as 3x squared dx in here, but then it might have been a little confusing, the fact that x is representing the variable here, but then x is also representing the upper limit. So I switched the integral to t's and then the upper limit of the integral to x. And so a hint of why we how we can visualize this is the fact that we use the letter a for this. That's a little hint. So why might we have done that? So go ahead and illustrate this integral for these values of x, 1, 2, 3, and 4, and actually make a table of those x and a values. Okay, go ahead and do that using your calculator now. Press pause. Okay, now hopefully you've tried this out and made your little table and values and found this. And what we're talking about, of course, if we're integrating, is to find the area. Since this is a positive graph, positive y values, or at least, well, I guess it hits 0 at one end, but never negative, then the integral is the area between the curve and the x-axis on that interval, or I guess this is the t-axis now. And so what we can do, one way we can do that with our calculators is on the TI-84, for example, is to do calc, which is second trace, and go down here and select number 7, which is our numerical integral, which of course in this case is an area calculator, and shader, not only calculator but shader. So it's going to ask you for a lower limit. You just type in it won't have the x equals, you just type in a number and it'll say x equals that number. So we want to go from 0 to 1, and then hit enter, and it's going to shade this area, and that's going to be a value of 1. So now we know when x is 1, then a is 1, which is this area. And of course that's why we use the letter a, as it stands for an area here. Now normally we would want to clear this drawing out by hitting draw, which is I think second program, and then just the first one, clear drawing. But in this case we're just going to be shading over the same amount, so we can skip that if we want. And then we do this for 2, 3, and 4. Okay? And so when we do it for 2, we're going to do this again, second calc, second trace, push number 7, and when it asks for a lower limit, this time put 0 again. An upper limit this time, instead of putting 1, put 2 there. It's going to shade a bigger piece, and it gets a bigger area of 8. Do the same thing for 3, and we get this area here, which is 27. I did change my window a little bit to go down to the negatives so that whenever it computed this at the end, it still showed the entire shaded area, and the answer was down here below. So sometimes when we're using this area shader, which is a approximation of a definite integral, and then it also shades it, it's useful to have some extra screen space. So I think I probably changed it from like negative 5 to 50 or something like that, or negative 10 to 50, something along that line. And then we also did this for 4 here as well, and got 64. And so these are a table of x values and a values. So as we change that upper limit x, we're changing our value of our input for this new function a, and the output of this new function is the area here. Okay, so the next thing is, can we graph this? Certainly we can graph these ordered pairs, but can we graph what the curve would be? Because, of course, x isn't just a whole number here, or an integer even. It could be any real number. So can we get our calculator to graph this? And hint, you can use your calculator's graphing abilities to do this. See if you can figure out how to do this, and come back when you think you've got it worked out. Press pause now. Well, what we're going to do is we're going to use the numerical integral of the calculator, which is function integrate in the old notation, or just the integral sign in the new one, and that will go from 0 to x, and then of y1 dx. Everything needs to be in terms of x here. Now that's Math 9 on the TI-84 calculator. In the older operating system, I don't have the screenshot for that. Okay, well let me go ahead and just work that out for you here real quickly. What the screenshot would look like in the older operating system. But meanwhile, while this is coming up, there it is. Okay, so we go to here. Let's clear everything out here. So y1 was our function 3x squared. Okay, this is in the newer operating system, so if I go to mode, even in the newer operating system, I can go to classic view, and you can see what this looks like in the old version. That, go to the y equals screen. Okay, that's what it looks like in the older version there. And this time when you hit Math 9, it comes up function integrate, or numerical, so function numerical integration. And so this is going to be y1, which you get by variables, right arrow to y variables, function y1, and then it's x, and then it's lower limit of 0 and upper limit of x. So this first one here is the integrand, what goes in the blank here. The second one is the variable x, which is from the dx here. The third one is the lower limit here, and the last one is the upper limit x. So this last x is the top inner limit. The dx here is the second x there. Okay, so that's exactly how that looks. In the older operating system. And either way, when you graph it, this is what it looks like here. Here we have 3x squared, the thinner one. I did make this a little thicker when I did it the first time here, and on the newer operating system. And here's the graph of this integral from 0 to x of y1 dx. Okay, so that's kind of interesting. Now let's zoom out a little bit so that we include all of 4 quadrants, a little bit of all 4 quadrants. Now, so far we've always done our integrals where we've gone from right to left, left to right, excuse me. So we've done where a, the lower limit, a was less than b. But if you reverse that, what happens? Well, remember that delta x, okay, is b minus a over n. Okay. In fact, let me go ahead and write that down like this. So to remind you that delta x is, well, in this case, it's going to be a minus b over n, which is the opposite of b minus a over n. So if you're integrating backwards where b is less than a, b is greater than a and going from b to a, so you're integrating essentially from right to left, you get a negative delta x, okay, in the underlying Riemann sum. So it turns out that you get the opposite thing. So the integral from b to a of f of x dx is the opposite of the integral from a to b of f of x dx. Now think about this particular example here. When we know what 3x squared is going to look like, it's just going to be a mirror image of this lighter graph over the y-axis, so the y's are always positive, or in one case 0. And so the integral from left to right of any piece of this is going to be positive. But we're integrating where the lower number is always 0. So if we go 0 and we put a negative x, we're integrating right to left, and so that's going to give you a negative value for its output. So that's why whenever we change our scale, this time I went from negative 5 to 5 on x and negative 50 to 50 on y. That's why over here for negative x's our output is negative. And we get something like that. What kind of graph looks like that? Okay? So what kind of graph would have that kind of shape? See if you can come up with a formula for that. And also the hint is it should fit these numbers here. Look at these numbers. 0, 0, 1, 1, 2, 8, 3, 27, 4, 64. And then this kind of a shape overall. Or you could look at the table some more. What is it? And whenever you get an answer, see if you can test it out. Press pause now. Okay? Well, if you work this out, maybe you came up with y equals x cubed for a. And we could check that out by putting that in y3 and check the tables for y2 and y3 and see, sure enough, they do check out exactly. So now the next question is, what's the relationship between a of x, which turned out to be x cubed, and f of x, which was 3x squared? Having had a little calculus already, we should be able to see a nice relationship between these two things. What is it? Well, hopefully you came up with the fact that one's the derivative of the other. In fact, the f of x was the derivative of the a of x, right? So you take the derivative of x cubed, you get 3x squared. So the f of x, 3x squared, was the derivative of x cubed. That's a prime, or the derivative of the integral of f of x, f of t. So what we did is we started by taking our original function here. We integrated it from 0x. And then we took the derivative, and we ended up where? Really right back at our original function. Very interesting. So somehow this is a reverse. So let's check this out using both numerical and differentiation and integration techniques. And so let's let y3 be the derivative of y2 with respect to x. Now if things work out correctly, this takes this process that we just did by hand using our derivative rules, and this is doing it approximately using calculator rules, calculator techniques. Actually, it's using a Simpson's rule for the y2, and it's using symmetric difference quotients for y3. But using these built-in approximation techniques, we can do this. So, and I turned off y2, so I just want to look at the table for y1 and y3. We hope that those tables should be the same, and of course they are. Notice right here at 0 you get something that's not exactly the same, but remember both this y2 and y3 are using approximation techniques, so these could be off just slightly. In fact, if I put my cursor here on this 12 and this 12, they might not be perfectly this exactly 12. One of them may be off slightly. Okay, well, the y3 might be off just a teeny bit. So they're going to at least agree to several places. Now, what if we change the original function to something else? Let's say 3x squared maybe plus 4. Did that change anything? Well, it certainly may change the values of y1, but notice the values of y3 were changed accordingly. Okay? Why don't you try this with some other function? Just make up any function you want. I just tried a couple of examples here. Seemed to work. What if you change the formula for y1 to just anything you want? Check it out. See if you do this. See if y1 and y3 still turn out to be the same. Well, so far that seemed to work. Did it make a difference that we started at 0? What if we try some other value there? Like here, I decided to start at 2, and I tried a new function, say ln of x. Did that work out to be the same? Well, if you look here, sure enough it did. Of course, this is negative 0.6 zeros in a 2, which is practically 0. So at least approximately, that worked out just great. So looks like this turns out to be the same in every case. You can check it out for several more and convince yourself that this is reasonable. And so the result that we got was it appears that we can take a function, integrate it from a to x, then take its derivative with respect to x, and we're right back at our original function evaluated at x. Interesting idea there. We're going to deal some more with this in the subsequent videos. In our next video, we're going to reverse the order of integration and differentiation. So here we integrated first, then we took a derivative. Next time we're going to flip it around. So come back for the next video as we do a little bit more with this.